Hello everyone. In this video, I'm going to talk about ways that we can measure central dispersion. I'm going to talk about the range, the variance, the standard deviation, and the coefficient of variance. So let's talk about what we mean by measures of dispersion. Now, a measure of dispersion is when you take a bunch of samples and you see how widely they are dispersed around your mean. Now, as you probably learned, the mean is a nice way to describe exactly what your values are, but it doesn't really give you a good measure of dispersion. So basically, when we talk about measures of dispersion, it's basically describing how similar each set is to each other. So if we have a bunch of samples that seem to be very close to the mean or more similar, we have a low value of dispersion. So that means that everything is kind of grouped around the mean. We don't get a whole bunch of stuff higher or a whole bunch of stuff lower. Now, another way to describe it is if we have a group of samples that are dispersed greatly around the mean, we see that they're less similar values. So if we have less similar values, the more spread out we have the distribution. So we call that a larger measure of dispersion. So let's talk about how we can measure that with the range, the variance, the standard deviation, and the coefficient of variation. Some of this might be a bit of a review to you, some maybe not. First of all, let's take a look at the range. Now, this is the most simple way we can measure dispersion. It's really the most easy to understand because anyone can look at the range of values and determine, what the extreme values are and the differences between them. So like if we have, for example, a range of values, that are kind of close together, the range would be lower than if we had a range of values that were farther apart. Now, what's important, though, is you can have a range that's different and still have the same mean. So remember that when we talk about measures of dispersion, it's a lot different than measures of central tendency. So here in the example 1, 3, 5, 6, and 7, we have a range of 6. Now, what we can do is, if you wanted, is you can actually take these numbers and rearrange them and get a smaller range and still get the same mean, actually. So basically, it's not really that reliable because we really can't tell how much of these values are above or below the mean. So we need another way to do that. So the way we do that is we take a look at two other different measures of dispersion. We can take a look at the variance, which is a deviation of each value from the mean, which is basically the average of the squared differences. It's called the least squares method, and it's really the topic for another video, but I can kind of describe it in very, very simple terms. Now, the variance works a lot different than the range because for the range, we're just looking at the dispersion of different samples or different observations and seeing basically what they are around the mean. But the variance, we can look at each specific value and determine how far away from the mean it is. So that way we can get a better number that describes, again, we're talking about descriptive mathematics. It describes for us the variance is a measure of how far the samples are away from the mean. Like for example, let's just say we have x. Remember, x is the observation. So we got 5, we got 10, we got 15, and we got 20. So before we can get a variance, we have to get the mean. So you know the formula to get the mean. All we'd have to do is just do sigma x, and we get something like this. So we get x bar, which is simply 5 plus 10 plus 15 plus 20 by 4. So we get x bar, which is the population mean, remember, of 12.5. So now that we got the population mean, is we subtract it from each value, and we get the absolute value. So that's by squaring it. So the 5 is 7.5 away from the mean, 10 is 2.5 away from the mean, 15 is 2.5, and 20 is 7.5. But we need positive numbers because we're not looking at if it's higher or lower than the mean, just how far it is from the mean. And we do that by squaring, which gives us an absolute value. So all we need to do is get the absolute value of the first one of negative 7.5, then negative 2.5, then negative 2.5 and negative 7.5, and then we get the variance. So what we do now is we get the we get the variance equals the following. And we could look at the variance, which is basically the standard deviation squared, which is the sum of what you see in the third column here. We take the square of the distance from the mean and we sum them together, and then we get what's called the variance, which we have here as the standard deviation squared. The Greek symbol is mu for that. So the variance gives us a better way that we can understand how values are separated around our mean, or how our values are dispersed around our mean. It's a lot better than looking at the range, but the variance doesn't scale very well. What happens is as you get values that are a little bit more dispersed as opposed to less dispersed, you don't get a real good one-to-one value. You get like a logarithmic value. So there's a way that we could take this measure of not central tendency, this measure of dispersion, and what we can do is we can look at what's called the standard deviation. Now, let's take a look at this again. Now, remember, the population is defined as all samples, and a lot of times we can't get all samples, so we don't look at a population mean because we might not be able to get the temperature of all 8 billion people on Earth, but we might be able to get a sample of 1 million of them. So that's the difference when we actually get a mean, the difference between a population mean and a sample mean, because the population is everyone or everything or every possible observation that we can do, which is often impossible, and a sample is just ones that we could measure. So the formula is almost the same, except look at the bottom equation. In the denominator, we have n minus 1. N is the number of observations. So the top formula you see in the right-hand side is the is the variance for your whole population, and the bottom is your variance for your or for a sample. So all you do is you take n minus 1, and that gives you the sample data. So remember, when you're getting measures of dispersion, it's going to make a difference, because to get that, you're going to need to determine if you're looking at the entire population, meaning that you're getting an observation for all possible observations, or if you're just getting it from the sample, and the sample is just a subset of that. Usually when we do descriptive statistics and descriptive mathematics like this, is we do with samples, because sometimes, as I mentioned, it's almost darn near impossible to get a sample from everything. Like, for example, if you wanted to sample the weight of every person in the country, you're going to be unable to do that. So anyway, so the variance formula, again, which is the mu squared, is we have, first what we do is we find the mean, and we're just kind of reviewing what we did in the prior example. And then what we do is we subtract the mean from each value, and then that's what we get for the second column. And then what we do is we square the differences, and then we sum them up, and we get the variance. Now, to go from the variance, as I mentioned before, a better way to measure this is the standard deviation. I think I might have got my symbol mixed up there in the previous example, because the previous example was for the variance. I think I might have slipped in standard deviation, so just ignore that. From here, what we're going to do is we're going to get a better measurement called the standard deviation. And the standard deviation, again, is just like the variance. It gives us a measure of how spread out the values are. But what we do is we get the square root of that. And by getting the square root, it normalizes our equation, and it makes it much more scalable. So as we get measures of dispersion that are closer to the mean and farther from the mean, the variance varies, pardon the pun, widely with that, where the standard deviation does not. So on the left here, you got the formula for the variance, and for the standard deviation, all as we do is we take that formula and take the square root. So it looks complex there, but if you look at that formula for standard deviation, it's really kind of taking a lot of those formulas that we already know and putting them together. So this is how it would look. I mean, to get the standard deviation, first you need the mean, then you need the variance, and then you need to square the variance. So here we got, in our example, we got each individual value observation, then we got x bar, which is our population mean. And what we're doing is we're looking at the distance from the mean in the second column. We're squaring it, right? And then what we're doing is summing it. Then we just take the square root of the sum, and we get the standard deviation. This is something that you're probably going to pause the video and take a look at. I'm kind of building that in. Let's take an example of this. Let's look at a river, and we got these different observations. So we could say, like for example, what is the average depth, which would be looking at the all the observations divided by 7, and then you can look at the standard deviation, which is how far these are away from the mean. So we have here for the standard deviation, we got our formula for our variance, and then we take the square root of our variance, and then we get the standard deviation of a real number, 3.55 feet. So we could say here that in this example, we have 7 readings and our riverbank. They have an average depth of 4 feet, and the average variation is 3.55 feet. Now, that could be, if it was smaller, that just would mean that we'd have a flatter river. And if it was a larger number, like 50 or 60 feet, we would have a river that would have like really larger peaks and valleys. So remember that the measure of dispersion isn't just pie in the sky numbers. They're actual real measurements that you could use in real life. Like here, we could use this for civil engineering, or we could use it for any sort of engineering project that might require building a bridge or doing pipelines underwater, something like that. So this is a good example I like to use, because this is an example that shows something that you would really use it for. We also have what's called your coefficient. Now this is also called your correlation coefficient, and this gives you kind of like a number between 0 and 1 usually that tells you how much variation you have. It's based on a percentile expression of the mean, and it gives you a kind of nice scalable number where the variance varies widely. The standard deviation gives you a real number in units that it dispersed from it. The correlation coefficient, the correlation coefficient gives you kind of like a fraction, like a percentile. Like 0 would be everything is exactly the same. 100 or 1, depending on if you divide it by 0, would be that it's as dispersed as it could be. Let me give you an example of that. Just to point out that each of these concepts that I'm talking about probably could be their own video. But let me take a look at ways that we can look at, for example, the 2 different methods here. Like we got a standard deviation of 4.8 and 4.0, but we could have a mean of method A being 120, and we could have the mean for method B of being 100. But this still doesn't tell us, if we compare them to each other, what the correlation coefficient is. And note, you could kind of ignore the analyte and the method there, because those are for just 2 different things here. So basically what we can do is we can look at method A and method B, and we can take a look at their correlation coefficient, or basically what does one have to do with the other. So basically we could take a look at this, and we can calculate the CV by being, in this case, 0.004, which is almost the same, where we just basically have the calculation of method A and method B, and when you plug it into the formula, we both get no more, neither of these are more precise than the other. So actually, we could probably spend a little bit more time on this. We're going to have more on correlation coefficients in upcoming units. But this is all I had for you today. Thank you for watching. Have a great day and be safe. Thank you.